This video will cover Keto-enol Tautomerism. First, let's consider some definitions. Tautomerism is the process of converting between tautomers, which are constitutional isomers that differ only in the position of a proton and pi electrons, and that can readily interconvert. Keto-enol Tautomerism involves a ketone or an aldehyde and its tautomer, the enol. These two tautomers can interconvert in the presence of either acid or base. In most cases, the keto form is more stable and therefore more favored than the enol form. In other words, typically this equilibrium lies very far to the left. Next, we will look at the mechanisms of interconversion in acid or base. First, we'll consider the acid-catalyzed tautomerism. In the first step of this mechanism, the ketone is protonated. The protonated ketone is resonance stabilized. In the final step of the mechanism, water acts as a base to deprotonate the carbon adjacent to the carbocation, forming the enol. Notice that the overall reaction is a protonation and deprotonation. This is because a tautomerization involves transfer of a proton from one portion of the molecule to the other, because tautomers only differ in the locations of the protons and pi electrons. In the acid-catalyzed mechanism, protonation occurs first, followed by deprotonation. In the base-catalyzed mechanism, we will see the reverse, deprotonation followed by protonation. In the base-catalyzed mechanism, the first step is deprotonation of the carbon adjacent to the carbonyl carbon. The carbanion that is formed is resonance stabilized. In the final step of the mechanism, the enolate ion is protonated to form the enol. Because keto-enol tautomerism causes the molecule to go through an sp2 hybridized intermediate, it can cause racemization at the alpha carbon. For example, let's consider this chiral ketone. If this chiral ketone comes in contact with a small amount of aqueous acid or aqueous base, we will see racemization of the chiral center. In other words, it will be converted to a 50-50 mix of the R and S enantiomers. The reason for this racemization is because in the presence of acid or base, a small amount of the enol form of this ketone is produced. In the enol form of this tautomer, the alpha carbon is sp2 hybridized. Therefore, the alpha carbon is planar and has no chirality. When conversion occurs back to the keto form, the proton can be added to either side of the double bond, giving either the R or the S enantiomer. Because the proton is just as likely to add to one side as the other, we get equal mixtures of the R and S enantiomers.